In this video, we will continue our discussion of parametric curves. At this point, we've introduced the idea of what a parametric curve is and also methods for visualizing. What we'd like to do now is talk a little bit about the associated calculus. That is, for a given parametric curve, what are the equations that we can use to represent the derivative, dy dx, and the second derivative, d squared y dx squared. So thinking about dy dx, what I'm going to do is just rewrite this ever so slightly. I'm going to write this as dy dt over dx dt. And essentially an intuitive way to think about this is that when you have a dy over dx, you do not have to think of this as a single entity. Instead, you can think of the separate differentials, dy and dx. So we multiply the top by 1 over dt, and we multiply the bottom by 1 over dt. And this is the formula that we have to represent dy dx. For the second derivative, we take a similar approach. And let me just recall for you that the second derivative would really just be the derivative of the first derivative. That is, we can compare to what we've done above and say that dy dx and the derivative of the first derivative with respect to x, those blue boxes really correspond. So we can think of this as being let me just call it y prime over dx. So dy prime, if we follow our method from above, should be the derivative d dt of dy dx. So you differentiate the first derivative that you've come up with respect to t, and then you once again divide by dx dt. And this is the formula that we have for the second derivative. Let's now put this into action through several examples. So for the parametric curve that we've seen earlier, x equals 5 cosine t, y equals 4 sine t, let's find representations for its derivative dy dx and its second derivative d squared y dx squared. So to begin, let's just remind ourselves what these formulas are. dy dx is simply dy dt divided by dx dt. And looking above, we have y is equal to 4 sine t. The derivative of 4 sine t with respect to t would be 4 cosine t. For dx dt, we have x is 5 cosine t, so its derivative with respect to t would be minus 5 sine of t. So this leaves us with minus 4/5, and cosine over sine is cotangent. So cotangent of t. And we will now use this first derivative to find the second derivative. So recall that this second derivative of y with respect to x, the formula is d dt of dy dx divided by dx dt. So the dx dt that we see appearing in the denominator is not something we have to do any extra work for. We take the denominator above and we rewrite it down, minus 5 sine t. The only new thing we need to do for this second derivative is to compute the derivative with respect to t of the dy dx that we found in the previous step. So that would be d dt of minus 4/5 cotangent t. So recall that the derivative of cotangent is minus cosecant squared. So minus a minus is going to make this 4/5 cosecant squared of t. So putting everything together, we have the minus 5 in the bottom, giving us minus 4/25. Cosecant, recall, is 1 over sine, so cosecant squared times 1 over sine ends up being a cosecant cubed of t, which gives us our second derivative. So one more very similar example. Let's find dy dx and the second derivative with respect to x. So dy dx, without writing down the formula this time, would be dy dt, so 2t plus 3t squared, just differentiating that parametric representation for y, divided by dx dt, so 2t. In this case, since every term present has a t in this, we could do a bit of simple algebra. We can write this as 2t over 2t plus 3t squared over 2t. So that dy dx is going to be 1 plus 3/2 t. And once we've found dy dx, finding that second derivative should be fairly efficient. So we differentiate, and I will write this step out, dy dx, and we divide this by dx dt. So dx dt is 2t, and the derivative of 1 plus 3/2 of t is 3/2. So doing some simple algebra here, so 3/2 over 2 is 3/4. Dividing by t is the same thing as t to the minus 1, or you could alternatively write this as 3 over 4t, whatever you find to be the most convenient.